Hello and welcome back. So, in the last class we were looking at steam water systems and we are going to continue to look at the same. So, we were looking for example at a system in A which contains water which we are heating at constant pressure, and then we saw that initially when it is only water the temperature increases, the specific volume increases slightly up to B, and then we reach the boiling point at B. After that we have conversion of liquid water into vapor. The volume increases quite a bit, the temperature remains constant during this process because the pressure is constant. And then we saw that after that we go from C to D where most of the liquid has become vapor and we have a little bit of liquid left at the bottom. The pressure is constant because we are using a piston cylinder system where the mass of the piston is fixed and the external pressure is also fixed. We saw that after that we reach a point E where all the liquid has become vapor. So, between B and E we see that the temperature is constant because the pressure is constant. In this entire process, the way we are doing it, we have a configuration where the pressure is constant and therefore, this is an isobaric process completely. But when you have an isobaric process and you have phase change, we have isothermal process during the phase change, which is what we see from B to E. And at E, all of this liquid has become vapor, and if we continue to heat it beyond that, we have an increase in the temperature which we see at the point F. And in this process, for the range of temperatures given, as we are heating it, the volume also continues to increase, which is also seen as we go from A to F. The volume increase is very small when it is in liquid phase from A to B. The volume increase is very large when you have a phase change from liquid to vapor, which is what we see from B to E. The volume change is moderate when we have only vapor phase, as we see from E to F. So, this is essentially what we looked at yesterday, and we saw that this curve along this point up to the top of it, which is what we call as a critical point, represents the boiling point for liquid to become vapor, and it represents the liquid at the boiling point. So, we called it the liquid line. This curve on this side from the critical point onwards towards this side represents the vapor at the boiling point. So, we call that as the vapor line. We call this as the liquid vapor dome. The top is the critical point where the latent heat of vaporization is 0. To the left of this liquid line we have liquid which is either too cool to be at the boiling point for a given pressure. So, we call it as subcooled liquid, or it is liquid which at a given temperature is pressurized so much that it cannot become vapor. So, we call it as compressed liquid. On this side over here we call this a superheated vapor because it is vapor which is at a higher temperature than the boiling point, and above this we called whatever is there as supercritical fluid, and we said that at these pressures it is difficult to make out whether it is a liquid or a gas, and we call it as a supercritical fluid. Far away to the right we said we have ideal gases, and we also said that the gases can be considered ideal if they are at temperatures higher than the critical temperature, but at lower pressures. So, if we go to more than twice the critical temperature, then we saw that the gases start to behave like ideal gases. So, we looked at this. So, we distinguished these as compressed to subcooled liquids, liquid vapor mixtures, saturated vapor, saturated liquid, superheated vapor. We have the critical point here, and this is what we call as critical supercritical fluid. So, we were looking at these on a TV diagram, and just to remind ourselves, when we looked at ideal gases on a TV diagram, we saw that the isobars on a TV diagram look like these pink curves over here. They are straight lines given by this equation. If pressure is constant, this would be a constant, we saw that earlier. So, on a TV diagram, an isobar for an ideal gas looks like this, whereas an isobar for a liquid vapor mixture, which we just saw on a TV diagram, if you look at the isobar, it is something like this. So, we see that this is not linear, this part is horizontal and linear, this part is curved, and as we go farther away from this dome, we finally reach the state where these become straight lines and they will start to look like this. So, far away from this liquid dome. So, for example, if I was to, this part is curved, let us say, and far away from here this is a straight line. Well, I am not drawing it very well over here, but you understand that it would be a straight line which would look like this. Similarly, if we have looked at PV diagrams earlier for ideal gases, we can look at isotherms on a PV diagram for a mixture of liquid and vapor. So, the liquid vapor dome which we looked at on a TV diagram now tends to look like this. On top of this, we again have the critical point where we have the latent heat as being 0. An isotherm over here goes down in this fashion. So, this would be an isotherm. As we go to lower pressures, you have this trend, or you could think of it as going upwards like this as you go to higher pressures. So, what we see over here is whenever the specific volume is very small, irrespective of what pressure it is, you have a liquid. We are not considering solids for the moment, we are only looking at liquid vapor states. So, when you have very low temperatures and you have low specific volumes, you would be in the liquid state at whatever pressure it is. As you go to higher temperatures, so as you go to temperatures which are higher, so this is a low temperature isotherm, this is a higher and higher and higher temperature. So, as you go to higher temperatures, you start getting vapor earlier. So, when you come from here, as you go to higher temperature isotherm, for example, if you take this isotherm, even at a pressure of around this, you have vapor, whereas if you are at an isotherm here, you will get vapor only when you come down to a very low pressure. So, that is something which we see. Within this liquid vapor dome, we saw earlier that if you are having a constant pressure process, the temperature is also constant. So, horizontal lines here would represent constant pressure processes because we are on a PV diagram. Within this two-phase dome, if the pressure is constant, the temperature is also constant. So, this would represent both a constant pressure and a constant temperature line. Once you go outside this dome, we have the temperature going down as the pressure goes down, and we have the vapor phase. So, what we see is just as the way we had a critical isobar, which is the isobar which passes through the critical point, here we have a critical isotherm, which is the isotherm which grazes this two-phase region and passes through the critical point and goes down. And if you draw this line here this way, this is our critical isobar which is horizontal on a PV diagram. So, above the critical point we have liquid and gas being indistinguishable. To the right of this we have vapor just as we did in the TV diagram. To the left of it we have liquid as we did also on a TV diagram. And for comparison, what we see is that if you have an ideal gas, this is what the isotherms look like. From the expression that PV equal to MRT, we see that PV is equal to constant for an isotherm, and they are rectangular hyperbolas on a PV diagram. We discussed this earlier. So, if you look at the saturated vapor line, which is the right hand side of the dome, it looks like this. When you are very close to it, these curves are definitely not hyperbolic, but as you go far away from it, which is to say that you go to higher temperatures, what we see is that the curves start to look hyperbolic and then you get ideal gases. So, this would be essentially be the remaining part of the dome here. So, what we see is that when you are very close to the liquid vapor dome, these substances, the vapors, do not behave like ideal gases, and what we would generally do is when you want to find out the properties of these vapors, we would take them from tables. As we go far away from this liquid vapor dome, the vapors start to behave like ideal gases, and then we can use the equation of state and find out relations between the various properties. So, this is what we see for on a PV diagram for these. So, we have been talking about a saturated vapor line and a saturated liquid line. So, a saturated state in general is a state at which there is a change of phase which may occur without a change in pressure or temperature, which is to say that if the pressure is fixed, the temperature is fixed, or if the temperature is fixed, the pressure is fixed. So, that would be a saturated state. The change of state can be either from solid to liquid or vice versa, or liquid to vapor or vice versa, or solid to vapor or vice versa. So, you can have any of these changes of phase which will occur. If there is a change between solid and liquid, we call it as a fusion state or a fusion line when we have this happening at different pressures and temperatures. When we have change between liquid phase and vapor phase, we call it as a vaporization line. So, we were so far looking at the vaporization line, and when you have change from solid to vapor, we call it as a sublimation line, or the process can happen in reverse also, where a vapor becomes a solid. The saturation temperature is the temperature at which vaporization takes place at a given pressure. So, we can find out this data from tables. So, for example, if you take water at 1 bar, pure water at a pressure of 1 bar, which is 0.1 megapascal or 100 kilopascal, then the boiling point of that water is 99.6 degrees centigrade. So, the saturation state for water, for the conversion of water to steam at 1 bar, is given as 1 bar and 99.6 degrees centigrade. So, in contrast to this, for example, if this is a pressure of 1 bar, instead of 1 bar, if we were to look at 1 atmosphere, which is 1.01325 bar, then we know that the saturation temperature corresponding to that pressure is about 100 degrees centigrade. And if when we are looking at say liquid and vapor transformations, what we see that if the temperature for a given pressure, if the temperature is below the boiling point, we call it as subcool. For a given pressure, if this is above the boiling point, we call it as superheated. So, similarly, for a given temperature, if the pressure is higher than the boiling pressure, then we call it as compressed liquid, and if the pressure is lower than the boiling pressure, it would be in the superheated state. If it is at the boiling pressure, both are saturated and you would be in the two-phase region. So, that is essentially what we see for these. What we can do is connect all of these points. So, for example, for water, we know that at a pressure of 1 bar, the boiling point is 99.6 degrees centigrade. For a pressure of 1.01 bar, we have the boiling point being close to 100 degrees centigrade. Similarly, at a pressure of 2 bar, we have, for example, close to 120 degrees centigrade and so on. So, we can join all of these points on a P versus T diagram. So far, we have been looking at TV diagrams in general. We initially looked at TV diagrams, and then we looked at PV diagrams. We can also look at P and T diagrams. So, on a P and T diagram, what we see is that during the conversion, the pressure and temperature are constant, or at least they are related, they are dependent on each other. So, if I keep the pressure constant, the temperature is constant. So, I do not see the two-phase region in the same way in which I can see it on a TV or a PV diagram. So, here once it reaches the boiling point, that point is just a point on this diagram, because I can only plot 1 bar and 99.6. So, that is just one point. Whereas, in the case of T and V, if I was at the boiling point, I can have the same temperature and different specific volumes as conversion takes place. So, we had a region which represented boiling over here, whereas only a point represents boiling. So, for example, over here this line represents the saturation line for a liquid vapor combination. So, for example, this could be a pressure of say 1 bar and a temperature of say 99.6. This could be a pressure of 1.01325 bar and a temperature of 100 degrees centigrade and so on. And this topmost one is a critical point whose value we will look at shortly, but the pressure is about 220 bar and the temperature is about 374 degrees centigrade. So, each of these conditions represents one point on this. But the nice thing about these diagrams, we call them as phase diagrams, is they can quickly give us a picture of the substance. This particular diagram is actually not for water, it is for a substance which contracts on freezing. Whereas, we know that in the case of water, as we freeze the water, water at 0 degrees centigrade has a higher density than ice at 0 degrees centigrade. So, water actually expands on freezing. We know that is the anomalous behavior of water. So, this is not for water, but I just used this part of the line to sort of tell you how this thing works. So, what we see over here is, if you have a certain pressure and the temperature is very low. So, let me take for example some line over here. If I have a certain pressure here, if the temperature is extremely low, then the substance is likely to be in the solid state, which is what it says. It will be here in solid state. At the same pressure, if I start increasing the temperature, at some point of time it starts melting. I reach the solid liquid line, it starts melting, and at this point initially all of it is at solid. If I give more and more heat, it becomes liquid. So, this point represents essentially whatever was similar to the dome for the conversion of solid to liquid. It represents complete solid, it represents a mixture of solid and liquid, and it represents complete liquid. All of it happens at the same condition of pressure and temperature, and after that the temperature starts to increase. So, if I am giving heat up to this point, the temperature increases at constant pressure because I am doing this process at constant pressure. Once I reach here, the temperature remains fixed and conversion happens from solid to liquid, and once complete conversion has happened, the temperature once again starts to increase and I get liquid whose temperature is higher and higher. This happens until I reach this point over here. This again represents a phase conversion point. So, at this point when I just reach it, I have liquid at that pressure. I am continuing to give it heat at constant pressure. What happens is that the liquid starts to become vapor. Initially little vapor is there, but the temperature is fixed. It does not change because I am doing at constant pressure. Afterwards, after some time, all of it becomes vapor, and once all of it becomes vapor, then the temperature will once again start to increase and I get to this side of it and I have vapor whose temperature is going on increasing. So, that is what happens if I do a process at constant pressure at this particular pressure. So, what I can see is that if I now do it at higher pressures, I have the same thing, but beyond the critical point I do not have the distinction between a liquid and vapor. So, I have just supercritical fluid over here, but if I do this process at much lower pressures, so if I do it at some pressure here, I have the same process as before, nothing different, but if I do this process at a much lower pressure, then I see an interesting thing. So, I have solid over here and then I reach this point and then it directly becomes vapor, okay, which is what we have as a process of sublimation. So, the solid becomes vapor without becoming liquid, and it remains vapor, and then it becomes, you heat it and the temperature of the vapor increases, but it remains vapor. So, this is one way of looking at these things. Another way of looking at it would be, for example, to look at what happens when I increase the temperature or when I increase the pressure at a given temperature. So, what we saw so far is what happens when we increase the temperature at a given pressure. What we can also look at is what happens when I increase or decrease the pressure at a given temperature. So, if I take for example a condition here. So, somewhere, let us say I am somewhere here, I have the temperature fixed, I am at a high pressure. So, if I pressurize something high enough, it tends to become a solid because I am trying to increase the density, the molecules get closer and closer. So, if I pressurize a vapor, it becomes a liquid. If I pressurize it further, it is solid. So, it is in solid state over here. If I reduce the pressure, the molecules can start to go farther apart, and if I am at some temperature in this range, as I reduce the pressure, if I go like this, at some point of time I reach this solid liquid line, and then the solid starts getting converted into a liquid. I am doing a constant temperature process here. As I reduce the pressure further, I still have liquid over here, but it is the liquid's density is now a little lower because it has freedom to move apart because the pressure is going down. If I reduce the pressure even further, then I reach this liquid vapor line, and then this liquid starts to become vapor. So, what I am doing is at a given temperature I am reducing the pressure. So, it is the equivalent of reducing the boiling point. So, what is happening now is that this liquid is starting to become vapor. Initially when it just reaches this point, it is all liquid. When it just leaves this point, it is all vapor, and as I reduce the pressure even further, there is vapor which is spread out more. So, it would be superheated vapor at this temperature. So, this would be saturated vapor at this temperature, this would be saturated liquid at this temperature. here it would be saturated liquid with respect to the conversion from vapor to liquid at this point. Here this would be saturated liquid with respect to solid to liquid conversion at that point. If I now take some other temperature condition, for example, if I take a temperature condition here, if I am going down like this, I have solid here initially. As I reduce the pressure, I reach this point somewhere, and below that it actually becomes vapor without becoming liquid, because I do not go into this region. Or if I was to look at the reverse transformation, if I was to go up, I have vapor here. As I compress the vapor, if I compress in this region, it becomes liquid and then it becomes solid. If I compress in this region, it directly becomes a solid. So that's essentially what we see. So this is for a substance which becomes smaller or contracts on freezing. So that we can see by the slope of this line. This line has a positive slope, and we can see that it contracts on freezing. The same curve for water is shown over here. Water is a substance which expands on freezing. We know that ice floats on water, so it must be having a lower density than water. So therefore, it must be expanding when it becomes ice from water. So this red line over here shows an isotherm. This is pressure versus temperature. It's our phase diagram. The red line over here shows an isotherm, and what we see is that this black line is to the left of this red on top here, and is slightly to the right at the bottom here. So it has a very slight negative slope in this region. So what we see is over here we have ice, solid phase. Here we have vapor, vapor phase, steam essentially, and here we have liquid water. In the ice we can have many different kinds of ice, different phases. We are not going to worry about those for the time being. But what we can see is over here we have, if I take a pressure of say 1 atmosphere, which is slightly above 100 kilopascal, which is like atmospheric conditions, we have ice over here, and we have the conversion from ice to water at 0 degree centigrade, and then we have the conversion from liquid to vapor at the boiling point, which is 100 degree centigrade at a pressure of 1 atmosphere. So this is what we call as a normal boiling point, and this is the normal freezing point of water. So again, in a similar fashion, what we see is, if I was to do this process at constant pressure, if I am at very low temperatures, I have solid ice. As I go to the right over here, I am increasing the temperature at a pressure of 1 atmosphere. I would reach at some point the temperature of 0 degree centigrade. At the temperature of 0 degree centigrade, I have melting of this ice. All of that ice melts. While it melts, because I am doing this process at constant pressure, the pressure does not change. But more importantly, while it melts, if the pressure is constant, the temperature also does not change. So after this melting process, I am left with water at 0 degree centigrade. So ice at 0 degree centigrade became water at 0 degree centigrade. After all of the water is formed, so after all of the ice melts, then this water starts to become heated, and then I can get, for example, to 20 degrees centigrade, and then the temperature keeps increasing till I reach the boiling point at 1 atmosphere, which is 100 degrees centigrade. There all of this water starts becoming steam. While this process happens, there is no change in temperature because the pressure is fixed. After that, I have the temperature of the steam increasing. So I have temperature here at say 200 degrees centigrade, here as 250 and so on. I have an increase in temperature, and it is all steam. So this process is what we saw earlier on a TV and a PV diagram, but we can now see it also on this. So the same thing happens, for example, if I take some pressure here, I have ice, then this green part it becomes water, and then in this reddish brownish part it becomes steam. But if I was to do this process much lower, for example at a pressure of 10 pascals, then what I see is I have ice here. As I keep increasing the temperature, it becomes ice at higher and higher temperatures. So finally I get to some point here, and after that the ice becomes steam. So it does not become water in between, the ice directly becomes steam, which is what we call sublimation, and then you have vapor, which is what we call steam as, and then all of this becomes vapor at higher and higher temperatures, but the pressure is still lower. So, we can have this process as well, and we do have the critical point somewhere beyond which we do not have a distinction between the liquid and the vapor. So, we call it a supercritical fluid. Like we were looking at in the previous diagram, we can see what happens when I take, for example, this line here. So, I have a fixed temperature of say 100 degrees centigrade and I reduce the pressure. So, if I am at extremely high pressures at 100 degrees centigrade, water would be in the form of ice, because it is in the form of a solid, because we are compressing it so much that the molecules do not have space to expand and move. So, you are suppressing it from becoming a liquid or a vapor. So, you can have, for example, ice at 100 degrees centigrade, though we never usually think of it. So, you can have that here, and if you were to reduce the pressure at some point of time, it would start becoming liquid. So, at this point it would start becoming liquid. So, when we get to a pressure of a little over say about 2.1 gigapascal, what we see is that this ice would melt and become liquid at 100 degrees centigrade, and if we this liquid is pretty stable. So, as you come lower and lower in pressure, it is all still liquid. It is 100 degrees centigrade, but it is still liquid, and as you come to a pressure of 1 atmosphere, then this liquid starts becoming steam or vapor, and it would get converted completely into vapor at this point. And as you come below it, you have vapor whose temperature is still 100 degrees centigrade, but whose volume keeps increasing because the pressure is going down, and you have superheated vapor in all of this region at the same pressure of at the same temperature of 100 degrees centigrade, but at varying pressures, at lower and lower pressures. So, that is something which we see. What is also interesting is to take, for example, some point here. If I was to take some point here and increase the pressure, what I see is over here it is vapor. As I increase the pressure, it becomes ice, it becomes solid. But because this line is sort of tilted like this, there would be a small region. So, if I was to sort of draw this portion of it a little magnified, so I have this black curve here, I have over here this line is slightly inclined to the left. I am going to draw it a little magnified so that I can sort of explain clearly what I am trying to show, and then this goes like this, and then this becomes like this. So, if I was to take some point here and I have pressure versus temperature, if I was to at a constant temperature, at somewhere here if I went, I would go from vapor to solid, which is the reverse of sublimation. But if I was to take some region here, I have initially vapor. As I increase the pressure, it would become solid. As I increase the pressure further, it would become liquid, and as I increase the pressure further, it would once again become solid. So, I have a small region because of the anomalous behavior of water, that it expands when it becomes ice. I have the small region where if I compress vapor, it would become solid, and then again if I compress it further, it becomes liquid, because ice has a larger volume than water at 0 degrees centigrade. So, if I compress it, it would become liquid, and then if I compress it further, then it would still become ice again. So, I have this strange behavior in substances like water. We have also what is called as a triple point, which is the point where we have solid, liquid and vapor all in equilibrium. So, in all of these lines we are talking of equilibrium. Any of these represents equilibrium between liquid and vapor, equilibrium between solid and liquid, equilibrium between solid and vapor, and so on, because at that condition we have both of them in equilibrium. So, for example, if I was to take at 1 atmosphere, if I was to take a vessel, fill it with liquid water and put in a lot of ice and insulate this, and the pressure is fixed, I have a piston so that the pressure does not change. So, some of the ice would melt. Supposing I could put water at 20 degrees centigrade and put a lot of ice in it, some of this ice would melt, and then the water becomes at 0 degrees centigrade, because the ice is at 0 degrees centigrade. After that, there will not be any melting of ice. So, the amount of ice I have and the amount of water I have after some time will remain constant. So, I know that they are in equilibrium because it is not changing. If there is any ice melting, then there is water freezing, so that this remains constant. So, that is what we mean by equilibrium. So, the same thing happens when I have, for example, liquid and vapor. So, in this piston cylinder arrangement, if I was to have a piston cylinder arrangement which is frictionless, and I fix the temperature, and I have some amount of water in it, some amount of vapor in it, if I look at it after a while, the amount of water and the amount of vapor will still be the same, the fraction will be the same, because they are in equilibrium. The water is neither evaporating beyond the net rate, nor is the steam condensing. So, steam is condensing at the same rate at which water is evaporating. It is in dynamic equilibrium, but the masses remain fixed. So, that is essentially what we mean as equilibrium. For all substances, there is one particular point where we can have liquid, vapor and solid, all of them in equilibrium, and that is essentially what we call as a triple point. There are many other points where we can have, for example, two phases of solid and one liquid, or three phases of solid in equilibrium. Those are there, but we are not interested in that. If you want a solid phase, a liquid phase and a vapor phase, then there is only one point at which all these are in equilibrium, and that is what we call as a triple point. So, we have the solid here. So, we are looking at the solid liquid line and the solid vapor line, the intersection of these, which gives us this point, which is called as a triple point. And for water, this condition is essentially 0.01 degree centigrade, which is 273.16 Kelvin, and the pressure is about 0.00611 bar, or essentially 611 pascals. So, for water, this is the triple point. So, you can have ice, steam and liquid water all in equilibrium only at this condition. So, if I have, for example, a piston cylinder arrangement, I have water in it and I put ice in it, and I want to have steam in it, and I do not want the fractions of these to change, I can have that only if I reach this particular condition. Similarly, other liquids have other triple points. So, this represents a triple point for water. For the previous case, this would represent the triple point where I have the intersection of the solid liquid and the solid liquid vapor lines. So, that would be the triple point which we are interested in. And the critical point is where the liquid and vapor do not have any distinction, which we see over here in the case of water. So, we see that the temperature is about 373.946 degrees Celsius, which is what I was rounding off to 374, and the pressure is about 220.6 bar. So, in Kelvin, the temperature is about 647 Kelvin. So, this is the phase diagram for water, and we have seen that for water, this part, the solid liquid line has a negative slope. For most other substances, this would be having a positive slope, where the substances contract on freezing. So, what we can also look at is isosurfaces of these. So, essentially whatever data is there, if you put it in the form of a 3D object, it would look like this. So, we have the PV diagrams, we have the PT diagrams, and we have the TV diagrams. All of them can be combined into these kind of surfaces. So, if you look at it from, say, from this side, so this is the T axis parallel to this T axis, this is the V axis. So, the TV diagram would look similar to what we were looking at earlier. So, we would have, for example, the liquid vapor dome, and we have liquid on that side, we have vapor on this side. So, that's and we have the critical point on top. If we are looking at it from this side over here, so the y axis would represent P, x axis would represent T, and we have the PT diagram. So, if you looked at it from this way over here, so you should be able to see, for example, the lines separating, for example, vapor and liquid. We have the triple line which passes through the triple point. We have the line represent the solid and the separating the solid and the liquid, and so on. So, we can see all of these on the same plot, and if you want to look at it from pressure and volume, then you have the PV diagram. So, that also is something which we can see. So, what we see over here is, for example, if I was to take some line at the same specific volume, or maybe easier it is to take same temperature. So, if I was to look at, for example, the same temperature, so I take something on over here, this line for example. So, if I have the same temperature with high specific volume, I am in vapor phase. The same temperature with medium specific volume, I am in the mixture of liquid and vapor. With a smaller specific volume, I go to liquid. Even smaller specific volume, I go to solid, and even smaller specific volumes, I am in the solid phase. Okay. So, that is essentially what I would have in this kind of a picture. You can take slices of this to get all of the previous data which we had, and what we can also see is that for a substance which contracts on freezing, which is what I had earlier in the previous slide, the plot looks like this. For a substance which expands on freezing, which is something like water, we have this portion of this graph essentially being different, and we can get essentially data of different properties. So, if we for example knew 2 of the conditions, we can find out the third condition from this. If we knew volume and temperature, we can find out pressure from this, and so on. So, what I was telling you earlier is that you can take projections of these, which are shown here a little clearer. So, if I take projections of this on a PT axis, I would essentially get this plot. If I take a projection of this on a TV axis, I would essentially get this. Okay, so, this is V and this is T. So, if I look from this side, I get the TV diagram, and over here I have, looking from the front in this direction, I have the PV diagram, and this is essentially the critical isotherm. This is going through the PV diagram. So, we can see all of this information from the PVT surfaces, which is quite interesting. What is also quite interesting these days is that you can find out the equations for these surfaces. They are available, or at least the data points are available. What is quite interesting these days is that if you have a 3D printer with you, you can actually print out the surface, and if you have a thread, you can actually put it along and find out properties. For example, at constant temperature, you can see what happens to the volume, or constant pressure, what happens to temperature, and so on. I do not have my model with me here right now, but maybe at some point of time I will try to put up some videos of it which you can look at. So, I am going to stop here for the moment, and we will continue in the next session.